everyone. Today we're going to continue with some max flow. A couple administrative things first. One, by popular demand, I went back and I did Lecture 7, Lecture 8, and now Lecture 9. All of those handwritten notes are online. My hand has a cramp from doing it earlier today, so please use them. If anyone who's complaining about it, you have to use it. Second thing is that I just released Project 2, the written portion. I've only released the written portion. I hadn't had time to make the coding outline yet, but you can start the code if you'd like. It should be fairly clear how the code works, although it will be a little bit hard to do without the visualization code that I'll give you. But maybe you can vibe code that. Cool, I think that's it. And then next week, so midterm is going to be on Thursday next week, not in class, just to be very clear. The time is listed on Piazza at 7 to 9. I forget the room, but it's in ILC, I believe, somewhere. Down the hall, I think. On Monday, we are going to cover new content that will be possibly covered on the exam. And then on the Wednesday before the exam is going to just be a review. So that entire class is just going to be a review. Yeah, I think it should be pretty clear what the topics are, by the way. We'll go through all the topics on Wednesday, but if you're studying, just look at the lecture titles on YouTube or anything. Those are the topics. So if you want to study, those are the things to study. Cool? All right, so we're going to start with a little recap of max flow. Just make sure that everyone's on the same page, everyone understands. Can someone tell me what are the components of a flow network? What's going on with flow? Yeah. Yeah, so we have a normal graph, like usual. Here, I'll actually just draw a single node, a single edge, I mean. So like a normal graph, we'll have all the nodes, all the edges, but each of these edges, instead of just having a single value like we had in the weighted graphs when we're doing MST, we're going to have both. It's also going to be directed, importantly. We're going to have both a capacity and a flow value. This flow value, what can this flow value be? What's the range of the possible values of it? So less than equal to the capacity, the C here stands for capacity. It also must be non-negative, so we can't have negative flow. It won't really come up too much in any of our algorithms, but we're not allowed to have negative flow. Cool. Greater than this, we also have that every one of these nodes has some other property. What property is that? We have some amount of edges coming in, each with them some amount of flow out of their capacity. What do we have? What condition do we need to have? Yeah. Exactly. So the sum of all the flows in, I'm going to denote this like the sum of all of the flow. I'll call this V. So this is for all nodes or all vertices out of the vertex thing. We're going to have that the sum of all the flows going in. So this is all of the things going to V is going to be equal to the sum of all of the flows going out of V, which I'm going to denote like so. So this is a sum over all output edges, and this is all output neighbors and all input neighbors. Cool? Is this true for every single one of our nodes? I did write for all, but a little caveat here, it is not true for our source, which is going to be a important node in our graph, which we're going to denote with S, and our sink, which we're going to denote with, of course, AT. So, we're going to have some amount of flow along all these edges, and our general problem is that we would like to have the maximum amount of flow going into T, or equivalently, the maximum amount of flow going out of S. Okay? That's generally the problem that we're going to attack, although flow networks, we could have other things that we want to do with it, hypothetically, but maximizing flow is the thing that we're going to do in this class. Okay? Now, we had a couple theorems that we came up with from this. Can anyone tell me any of them? What theorems did we come up with? Sure. Okay, so this is the broader theorem. So we had an original theorem, which was just that there exists for any max flow. So in a max flow, there exists some edge such that the flow of this edge, I'll just write it like this, the flow of this edge is equal to the capacity of that edge. Right? That is, it is saturated. Later on, we realize that we can extend this and say something a little bit stronger. We can actually say that there exists some ST cut. I'll write it like that, I guess. Some ST cut such that the sum of the flow from S to T, that is from every node in S to every node in T, is equal to the capacity of this, the capacity of each one of these, and also it is true for every single one of these edges. So not just that the sums are equal, but in fact that all of the flows are equal to the capacity. That is, every edge along this ST cut is saturated. Now, ST cut is a concept that I think is still confusing a couple of people, so I want to take a second to remind us all, what is an ST cut? Can someone tell me? Yeah. Exactly. So it is tempting to think of a cut as a physical cut through the network, like so. But in fact, it is more accurate to say what we're doing is we are assigning every node either to be in group S or to be in group T, with the only exception being that S must be in group S and T must be in group T, hence it being an ST cut. Okay? So there exists some ST cut such that the flow across this boundary is saturated. That is, every single one of these edges that is going from S to T is fully saturated. Okay? We had one other theorem. Anyone remember it? We actually used it to prove this. We used it indirectly to prove it. Yeah. Exactly. So for every ST cut, so this is for every ST cut, this is for all ST, we have that the flow of this ST cut, flow from S to T, are all equal. I'll just say are the same, to save myself some notation. So I'm saying that every single one of these ST cuts I would take has the same amount of flow going from the S side to the T side. Okay? We had a small little, so the reason that this happens, you can prove this differently than I'm going to explain, but I'll explain the intuition. We can think that anytime I have one of these cuts, if not all of the flow is crossing this cut, then it must be staying in the S side somehow. If there is a flow over here that is greater than on this side, right, there's flow that's not crossing, but there is a greater flow over here, then I know that some flow must be being made over here. And because of our condition that the sum in equals the sum out, this cannot happen. So because of this property, we can get this bottom theorem, and then from that bottom theorem, we can then derive the top theorem. This top theorem, by the way, does have a name that you may hear referenced, so I'll say what it is. This is the min-cut max flow theorem. So you may hear it called this. That is that theorem. Okay? It may actually be max flow min-cut, but same deal. I think it's min-cut max flow. When we say min-cut, by the way, that is minimum capacity cut. That's something that I didn't actually say explicitly on here, but this cut, the SC cut that exists, will also be the cut that has the minimum capacity, the minimum total capacity from S to T, on edges that go from S to T. Okay? Okay. Any questions on this? This is totally the amount that I'm going to recap flow. I'm going to now talk about new things. So if you have any problems with this, let me know right now. Okay. You can still ask while I'm erasing also. Okay, so we have these theorems. We'll hold on to them and consider them perhaps later. So now, the question is, how do we find a max flow? Does anyone have any ideas? So if I have some graph, I'll come up with some arbitrary graph here. Let's say this is 100, 100. So right now they have no assigned flow. We'll say there's 0 right now. Another one, and another one here. so that each of these are 0 out of 100 also. And why don't we add another edge here in the middle that just goes down and has capacity 1. Say we have something like that. You maybe will realize why I made my graph like this. So if I wanted to find the max flow, it's pretty easy to see, like, oh, I could send 100 on the top, 100 on the bottom, max flow would be 200. But how could I find this algorithmically, and how long would it take? So any ideas of how I could do this? I'm seeing too many familiar hands. I want people to think on this for a second. I'll ask you a different question to maybe help with this. Let's imagine that I had, instead of just zeros, right? Let's say that I assigned some flow to start. Let's say I had like 2 flow here, 1 flow here, 1 here, and 1 here. Okay? Say I started with that. How can I increase the flow? I'm going to give you a little bit of time to think about this. I want you to maybe come up with this on your own. This one is not that bad to come up with on your own, but it requires a little bit of an insight. I'll erase these now, but we'll remember them. They're good ones. I'm not going to ask you to know by name, but you should understand how these sorts of networks work well enough that you can know those theorems, sort of by knowing them.
We're not just talking about, oh, right, and then you're supposed to apply them.
It's hard, not a memorization. You're searching for I memorize it, you memorize it, it will not Oh, yeah. Yeah, sure. You talk to neighbors, give it a minute, see if you can come up with something.
And then if you find a path, then you just find the maximum capacity of power and just eat all that 30. You just add more to the
Okay. I'm gonna cut you off there. You'll get a little bit more time to think about other things, don't worry. Maybe even some slightly more difficult problems. Anyone have any insight as to how we could approach this problem? Not necessarily a solution, but just any insight of how we could approach it. Called on you too many times. I want to see someone I haven't seen before. I do have the prize bag actually here. Someone who hasn't raised their hand today can get a prize. Yeah. You raised your hand. Oh, you wanted to give out prizes? Yeah. Okay. I'll let you do that if you tell me something about this. Something about SC cuts. That's a reasonable guess. We're going to not be doing that, but that's fine. Here you go. You can give out prizes. There's not very much left, by the way, because I had to buy them and I'm broke. Any other ideas of what we could do? SC cuts is a reasonable approach, a reasonable thought. Yeah.
Make the top one that's 2 out of 100. Set that to 100 first.
Okay, so we can sort of push the flow, as you might call it. So we would say load this one up and then see where it can go and repeatedly do this. This will result in an algorithm, but not one that we're going to talk about today. We might talk about it next Monday. That one ends up having a lot of nitty-gritty difficult details to try to make it work. Yeah? Any, right? This is an example that would maybe be insightful about this. So, yeah. So the suggestion here is basically that we do a search. And as we do our search, we have our flow and we have it and we kind of push it forward like you're saying. The problem with this is it isn't necessarily true that there is a path where I can add any flow. Like for example, if I remove this and say this was a higher capacity edge, your algorithm would go here and go, oh, this one's already full, I can't do anything. And it would fail. So you need to have some way to guarantee that you can add the flow. But here is sort of the first thought here is I want to find some way to add flow. Right? I want to take some way that I have this graph and I want to find some path where I can push flow through. Okay? So here's going to be what we're going to do. We're going to take this graph and we're going to construct a different graph that contains all the information of where I can send flow. Let's think about this for a second. If I have a node, an edge like this, and it has some amount of flow out of its capacity, then how much flow could I send forward? How much? How much more could I send forward? C minus F. So I can say I have the possibility to send forward C minus F. How much flow could I remove from this edge? F. So what we're going to do is we're going to create a graph where each one of these edges becomes one of these pair of edges. We're going to say that this graph, we're going to name it the residual graph. So this is our original flow graph, and then we're going to create what we're going to call the residual. Residual as in sort of difference or leftover, if you're curious. So in this graph, I'm going to take each one of those edges and I'm going to separate them into these two different types of edges. So for example, this first, which is 2 out of 100, what does it become? What's the forward? Just shout it out. I think people can do the math. 98. And backwards becomes 2. All right? This one right here, you'll notice, only has a forward edge of 100. There's no backwards edge because it's already at 0. Right? We can still send everything. We can't take anything back because it doesn't have any flow. The middle edge, similarly, is reversed. It is allowed to remove one flow, but there's no more flow can send. It's already saturated. And lastly, the final two are somewhat similar. It's 99 and 1, and similarly 99 and 1. Now, are there any properties about this graph that we can use? Any ideas? You're on your cool down period. I'll call you again later when there's harder questions. Anything we notice about this? Remember, what I want to do is I want to find a path where I can add flow along that path to increase the amount of flow. So what can I do? Yeah?
Can't you just...
Yeah, so continue from that thought.
So... That's what you already have?
I appreciate the attempt. Sort of, but we need something a little bit stronger than this. Remember, what we're trying to find is some path in the original graph where I can add flow. Right? So what could I do? Yeah.
That would be a path. Like, for example, the arrow would be 1 in it.
Okay, okay.
So we just do a search and then...
Okay, you got close enough there that I'll call it. You want to say something? Yeah.
Should we just focus like on a forward
There's a reason that we have both. I'm not doing nonsense here. Also,
like after.
yeah. Afterwards? So what we're going to do, we're going to get a single path and then we're going to augment this. We'll get there in a second. By the way, can you turn around and tell him to get off his phone? Pocket, come on, pocket. Yeah. Yeah. Anyone want to say a full-fledged now open to anyone who has the idea, yeah? So what we can do is we just take our residual, and I'm going to postulate now that if there is a path in my residual, there is a way that I can increase my flow. Okay? Anyone see why this is? Let's say I find some path. Let's go with, for now, let's go with this one right here. The 100 and then the 99. So there is some path from S to T. What does this tell me? Well, I can take these values, right? So I know that there's some path. There's at least a way here that I can add flow. That's exactly what the residual graph means, is that this is a way that I can change my flow. Right? So if I have this path, I can add them there. So would I add 100 to this one and 99 to that one? No, I would not. So you'll notice if I do that, this would end up 100 out of 100, 100 out of 100. This has 101 going into it. I'd violate my original assumption. So I need to add some, I need to find a path, I need to add some augmenting path from it, is what we're going to call it, such that it obeys that property still, that the input and the outputs are equal. So what value could I add to each of them? Exactly, the minimum of them. So what my augmentation here would actually do is I would add 99 to this one and to this one. Okay, so that would be my augmenting path. And then once I do this, I'll end up with some new flow network, and I can make a new residual. Okay, so now I go here, and this one is now fully saturated. It can send 100 this way. And this one, you can send only 1 forward and 99 back. Right, so that's our new residual graph after I make this augmentation. Now, can I send more flow? Yes, there is still a path from S to T in this graph. Look right here. So I can take this path now as my augmenting path, this top lane right here. And how much can I add to those edges in my original graph? 98. So I can add 98 to each of them. And what you'll notice is that this is going to come out to giving me, this is 100 out of 100. This is going to be 99 out of 100 for now. This is going to be 99 also, and then this is going to be 100. Okay, so this is my graph right now. Okay, now just looking at this, is there a way that I can send a little bit more flow? How? Well, let's go back to the residual. So this is now going to be fully saturated, so this is just going to be 100 backwards now. This is going to be 99 backwards and 1 forward, so we're going to flip those two. Right, so this is only going to be 100 backwards. This is going to be 1 forward, 99 backwards. What's the path from S to T? Go this way, right? If I change those, what we'll end up with is 100 on the top, 100 on all the 100s, and 0 on the 1, right? You'll notice when I add this, right, this flow going this direction, I'm subtracting from here, by the way. Importantly to note that. Okay, so to describe the overall algorithm, you have a question?
What's the residual?
The residual is this graph. So it's the graph where we do the following procedure to each one of the edges, right here. When we do that, it becomes a residual graph. I'll specify, I suppose, that it's a residual graph. Residual network, whatever you want to call it. Sometimes I will say network, sometimes I'll say graph for these type of figures. They are both, in a way. We call them network flow. But they are graphs. They are graphs. It's fine to call them that. Okay. So the overall procedure for this algorithm is going to be, we take our graph, we're going with whatever flow it has. Generally, we're going to be given something that has 0 initial flow, but sometimes we'll have initial flow. We're going to create our residual graph. We will run some sort of search, let's say DFS, to find some path through here. Then we're going to find the minimum weight along that path. That will become our augmenting path, right? That much weight along each one of those edges. We make our updates appropriately. If it's going the opposite direction to our original edge, then we subtract. Otherwise, we add. That makes sense? And what we're going to do is we're going to repeatedly do this until there are no paths in the residual. Now, question for you. If I do this procedure, will I necessarily maximize flow? We know that we'll end up, yeah. Who thinks we will? Who thinks we might not? Who thinks we could end up in a graph where we can't add any more, like the residual doesn't have a path, but we haven't reached max flow yet? Okay. So as it turns out, I mean, it's fairly easy to guess since I've spent so much time on this algorithm. This algorithm is going to work. So this algorithm, we have a couple things we need to prove to show that it does work. I'm going to be a little bit lighter on the proving for this algorithm, so we can spend a little bit more time on the proof for the next one, by the way. This one is fairly intuitive, and if you'd like to prove it on your own at home, it's actually not too bad. For this, though, first we have to prove two things. One is that I'm going to just put these two things as lemmas So lemma 1 is going to be that if there exists some path in the residual, if there exists a path in the residual, I'll say like that, from S to T, I'll say it's ST path, path from S to T in the residual, then the flow is not currently maximized. So that is the flow of the network is less than, strictly less than, the maximum flow. Okay? So that means if I have one of these paths, if I augment it, I will, so that means that if I find a path here, I can increase the flow. When I add this augmenting path, I will necessarily increase flow. It's sort of a given just by the nature of this. But it means that if there is a path, then I do not have maximum. Second thing is that if I do not have a maximum flow, so if flow is less than the maximum, then there exists a path in the residual from S to T. So what I've really shown, these two together, you might realize from your logic in the residual, from your logic training in 250 and all this, this is just showing that these two statements, that there exists a path in the residual and that we do not have maximum, are equivalent. Okay? And if we show those two things, then we know that, in fact, if I continue to do this, that every time I take one of these augmenting paths, I will increase the flow in my graph. Necessarily, if there's a path here, I can augment by at least one, I know. Then, as I continue to increase them, as long as there exists a residual path, then I know I can continue to increase it, and as long as it's not maximum, there will be a path in the residual graph. Hence, if I continue this procedure, this will eventually reach a maximum flow. Does that make sense? So every iteration of this increases flow, and I can do another iteration as long as I don't have max flow, is what I say with these two lemmas. I'm not formally proving them, but you can see why they're true, probably, through intuition, and you can spend a little time proving them if you'd like. Okay? Cool. So this algorithm right here is going to be called Ford-Fulkerson's. Okay? So all of this procedure, where I'm finding an arbitrary path here, and then I'm creating the residual, finding a path in the residual, finding an augmenting path, finding the minimum weight along that augmenting path, changing my graph, and then creating the residual. And repeating like that is called Ford-Fulkerson. And I'm going to ask you, yeah? Can I read them out loud?
No, can you read?
What's the difference between them is the implication. So the implication is saying here. So this is saying existence of a path in the residual from S to T in the residual implies that there exists a that the flow is not maximum. Flow is less than maximum, and this is saying that if the flow is not maximum, that implies that there exists some path from S to T in the residual. Okay?
Could I not make the second if?
So you're asking why can't I just go directly to saying that these two things are equivalent? You can, but generally when you want to prove statement A is equivalent to statement B, it's easier to do it in two cases rather than do it at once. You'll find that trying to do it at once, you'll end up just implicitly doing this with a little bit more of a headache. So a little bit of a proving tip for you is generally if you want to prove things equivalent, prove both these cases. Yeah.
Can you explain the very last step again? Like, how do we know to take away the one?
How do you know to take away this one?
Yeah.
So what we do is we find a path in our residual. The only path from S to T in this residual is this path right here. That gives us our augmenting path. And if we go to our original graph, so I'll mark these in red. And if we go to our original graph, we find those same edges here, 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 along this direction. And for each one of them, we add one flow going that direction. Okay, so what that means here is we're adding 1 to this, which will make it 100. For this one, because it's sending a flow this way, we're removing that flow. This becomes 0. And then this one adds one more, it becomes 100. Okay?
Yeah. Thank you.
So that's sort of the interesting insight here is algorithms like what was suggested over there, like the sort of pushing type algorithm. You won't necessarily get this behavior where I remove a flow. But it turns out that removing these flows sometimes are the only options of how to augment my graph. So it's important to have something that can capture those. Okay, question? That was about to be my question to all of you. So now, think. What is the time complexity? You can assume that for the search we're using DFS, just to make your life easy. What is the time complexity? In particular, what is the worst case scenario? Everyone, think about that. Backtracking, there's no, for flow networks, there's no edges that go both directions. We'll never have that in flow.
And
The residual is not a flow graph. The residual is just a different graph. Yeah. For this problem, by the way, I'm going to reset this, because this graph is going to be a good example for us. We can look at the residual and think about it. We'll set all these back to 0. What does our residual look like? We just have our forward edges. It'll be exactly the same graph, except with no flow along any of these edges. So it'll be 100 here, 1 there, 100 here, and 100 here. Okay. So it's possible, I think we can all see that I could just do this path and then this path. What's the worst case scenario? Here's a question for you. How much flow do I add when I take one of these paths? When I find one of these augmenting paths, how much flow am I adding to my flow network when I change it? Yeah. The minimum along that path. So the number of iterations I have to do is somehow going to be the maximum flow divided by, I suppose, the amount of flow I add each time on average, right? So what is a worst case scenario for us? We know that doing an iteration, we add at least one flow, always. Because if there exists a path, it's only in integers. We don't deal with decimal places. It's at least one. So what would be the worst case scenario? What would create the highest number of iterations that we need to do? Yeah? So if every iteration, we only add one flow, let's see, can we do that here? Well, if I were to find this path, this red path right here, then because the minimum edge along this path has capacity 1, or has weight 1 in this graph, that means I'm going to update each one of these only by 1. So this will become 1, this will become 1, this will become 1. I'll remove these to not distract. So then if I go draw my residual, what ends up happening is that this edge will now become 99. This will become 1 the other direction. And this one will become 99, and 1 backwards on each of these. Okay. Now, is there a way that I can add 1? There sure is. I can go this direction now. So now if I update that, that would give me 1 here, and now 0 here in the middle. Okay? What you notice is I can keep doing this. I can just alternate between that first path and that second path, mean that every single one of these is going to only add 1 flow. So how many times do I have to find an augmenting path? Yeah. In this case, it's 200, but more generally, it's going to be the same as a maximum flow. And how much time does it take me to find an augmenting path? Remember, I'm using DFS. Sure. No, behind you. It's going to be E plus V in general. So we're going to say that this will take to find one of these paths, we'll say that DFS is going to take V plus E, which, because we know the edges are going to be higher order than, or going to be equal or higher order to the V, we actually say that this is going to be order E. If anyone has a problem with that, raise your hand right now so I can answer that question. No one has any problems with that? Yeah? You have a problem with that? So the number of vertices must be smaller than or equal to the number of edges minus 1. So because the number of edges, basically every vertex will have an edge. You sort of get that logic? Then the amount of vertices is going to be at most the number of edges, meaning that this is going to be less than or equal to 2 times the number of edges, which is order E. Does that make sense? Because vertices are smaller, the number of vertices is smaller than the number of edges. So this doesn't matter. This is the part that matters. Okay? Anytime we have V and E, E is the bigger one, unless we have a very, very, very sparse graph, which we will not assume. In fact, we'll assume the opposite, otherwise all of our algorithms are meaningless. So, we're going to say that this is O of E, and we say that we have to do this the same number of times as the maximum flow. Therefore, what is the runtime of our algorithm? Sure.
E times max flow.
It's just going to be Ford-Fulkerson, I'll write it over here, is going to give us order E times the maximum flow. Yikes. What's the problem with that? Why do we not want that? No, it's not necessarily n cubed. Also, n doesn't mean anything here. You mean vertex cubed or e cubed? The problem is, sure, would you like to explain?
Your flow doesn't
Exactly. So for one, it doesn't matter how big the graph is. Our algorithm can take a very long time. Worse off here is that a somewhat arbitrary thing, the maximum flow here, the maximum total capacity along like the minimum cut, is going to be directly affecting our, linearly affecting our runtime. That is not a good behavior to have, because now I can create some flow problem where these values are, 10 to the 100th. I can make them whatever I want, and I can make them exceptionally large. So that in the real world, even you can run into the situation in the real world. I know you're unlucky here, but you can run into something like this, where then your runtime just is enormous. It's enormous based on this sort of this property of the problem, which sometimes can be extremely high order magnitude. There are flow problems where I might want to convert a problem into a flow problem and solve it using flow, where the capacities are going to be enormous. Now, that doesn't mean that necessarily that's not a good thing to convert to that algorithm, but it just means that Ford-Fulkerson, in the worst case, can be horrendous. We really, really don't want this sort of behavior for any sort of efficient algorithm. I'll tell you now, on project 2, if you try to use Ford-Fulkerson, it will be very slow. Okay? So, what can we do to speed it up? Well, let's think about the very simplest thing we could do. Okay? How can we change this procedure to try to make it faster? Any ideas? Give you a second. Give everyone a second to think. How might we speed all of this up? So there is the time that it takes us to find an augmenting path, and there is the number of augmenting paths that we want to find, right? Which one do you wager we could actually decrease? Could we decrease the amount of time it takes us to find an augmenting path? Not very likely. If we know much about search algorithms, it's unlikely. Perhaps there's something we could do by finding specific types of paths in the residual, but it doesn't seem very likely. So instead, we might want to decrease the amount of iterations we need to do somehow. Any ideas on this? Yeah. Mm-hmm.
Again and again. Or avoiding paths we've already.
Okay, so the core idea of what you're saying is basically avoid already chosen paths. Maybe back to back, you don't allow the same path twice in the residual, something like that. So there are going to be cases where we have to do that, just for the record. So there are situations where we cannot avoid repeating the same path in back to back. Basically, one path can block all other options until we free it back up. So we have to be a little bit careful with that, but I like where you're headed. Anyone else? I'll wait until I see it back there. So we could prioritize the largest, so I'll more generalize this. I'll say choose the largest augmenting path, the one with the highest minimum. Any guesses what that runtime would be? So it is tempting to think that if I did that, I would necessarily get a speed up, because if I were to do that, then at the very least, I'm not getting 1 every time, which is a fair enough argument. But what can end up happening with that is that you take some large path and you actually block it off in such a way that this behavior happens again, that you need to take a bunch of 1s over and over and over again. That you can do slightly better than this. It's not exactly like that, but it turns out to not be as good as you might think, strangely. So that algorithm, I think I'll give you the runtime of that. I have it written down here somewhere, I believe. I do not have it written down here, but it is something like, do not take this as fact, by the way, but it's something like E log V plus log C, where C is the largest capacity of the graph. Okay? So we still end up with this reliance on this factor that is totally arbitrary, that could be totally out of scale with everything else. So we need to be careful. This is a good idea, and it does produce a better algorithm, but there's something even more simple that we can do that produces a much better algorithm. Okay? Not much better objectively, but it's better than this. Better than this. Any ideas? Yeah.
Okay, so this is kind of ideal, but like these algorithms, I noticed depends on like.
Yeah. Yes. The time complexity when we're talking about graph algorithms will always depend on the number of vertices, number of edges, and sometimes other features like you just saw there, like the capacity. Some other things we might see is the average degree, like the average number of neighbors, or the max degree, stuff like that. We have algorithms that depend on them. Here's what I'm gonna suggest. What if instead of choosing the maximum augmenting path, what if we always choose the shortest augmenting path? So this is the core idea of Edmund-Karp. In Edmund-Karp, the only change we make to this is that instead of running DFS, we run BFS. That is, we find the shortest possible path from S to T in the residual graph. Okay? Now, I am going to open this up as a little bit of a, call it today's pseudo quiz. I am going to give you some time to consider what the runtime of that algorithm will be. As we go in this little working period, I'm going to give you some hints to help you along the way. If anyone can beat me to the punch and tell me what the runtime is with proof, I'll give them 3 bonus stars. Okay? So whoever can get it first. It is totally feasible to get it, but it is a slightly tricky proof. Everyone, even if you are thinking, oh, I'm not going to get it, attempt this problem, because it will be a lot of good experience for something like the test next week, where you have to prove something that is somewhat difficult. Okay? So, go. Same as DFS. Runtime for BFS is the same as DFS, by the way. It's V plus E.
Yeah, because like worst case scenario, this is always fine. Yeah. No, I'm saying like the whole algorithm.
No, but like look at this difference. What messes us up is that we take that one that goes 3 and then we do it 2 and 3. If we use BFS, we get a pattern of 2, which in this case would be much better.
But what if the graph had 100 equally like paths to all capacity? Yeah.
Well, then that determines the number of edges. The arbitrary.
One scale of things you could have like no edge. That's a 0 fact.
It's gonna take a lot of time to tune the drain.
But it's still, like, let's say all these edges have capacity one, right? But it wouldn't be an edges because you can just arbitrarily scale the graph out by just making it so.
Okay. First hint. Lemma 1. Altering the flow graph with any augmenting path from S to T will saturate at least one edge. That's hint number 1. Continue. So I'm giving it to you as a fact, so it's okay.
That's okay. So here at max,
Very easy to prove.
like
Oh, you're saying, in my example, you have to add more nodes versus
which is okay.
which is,
Or like not really like you know that
well, it would scale off the number.
yeah, which is like it's not
Because that would, if each path, like, worst case, each pathway, you need to figure out when and saturate it.
yeah, the whole point is we just want to know
Because if you're saying that, like you could saturate one, but by doing that,
Augmenting paths are when I found a path in the residual,
I guess
and then I added to all of those edges the minimum of that.
but not specifically edges.
The minimum. So here, right, there was like 199. To this edges I added 99. The minimum of all of the entities.
Because CFS is still like reused. I don't know, that might be crazy. I think I have it. Tell me if it's no.
That'd be super fast.
I was hoping. It's like no way though.
No.
So what you're doing with like
You're finding a path in the residual from it. That tells you how I can change my flow.
And you have to
So the residual is how I can change my flow. If there's a way I can get it such that more is going to then that's it.
like why does it not do the like if you want to show now that it's guaranteed to
Maximizing the
at all if we always get the shortest path. If the 10 out of 100
taking that one my intuition. Because that would be wrong. Right? Like in this example, the only reason why we're changing that is like yeah, I know, but I'm saying that we won't be able to take that because it's longer than each of the past individuals.
That's the whole idea. That's the whole intuition. At least for that example, that's why it's doing it with different stuff. And then the question is like, why is it always
Like because it's equal to
like
the flipping path will always be equal to you'll probably need either of the paths plus or will always be equal to
Okay. I'm gonna give you a second hint now. Second hint. This is a bigger step of a hint, by the way. So lemma 2. Lemma 2. If the shortest path that saturates some edge E, so let's say if the shortest augmenting path Log path to saturate E is length D, then after applying that augmentation, the shortest path to unsaturate that same edge is D plus 2. So D, I heard that. D is the length of the shortest path. Here, I'll use. This is a much more complicated lemma. I will in brief prove it actually. Let me check the time. Make sure I have time to do that. Yeah, we got a little bit of time. So here's a short proof of this fact. So imagine that we have some path from S to T. Some path from S to T. This little thing here means some arbitrary path, and this will go to some U. So this is S. It goes to some node U. U is connected to some node V somehow, and then there's some path from V to T. So what I'm saying is, let's say that this edge UV is the one that's being saturated. So this is an augmenting path from residual. The edge UV is the one that's being saturated. So once it's saturated, then in the residual, it'll now be facing backwards, right? That makes sense? So once I saturate it, it's only able to send flow backwards. Everyone okay with that? So this is like in the residual, it'll be facing backwards now. So now in the residual, if I want to have some path that unsaturates this, then it needs to be a path from S to T that goes from V to U. Okay? So you're vigorously shaking your head no at this. Okay. So in the original graph, I have this path, right, from S to T. Let's say this is the original augment. We'll say this is residual 1. I have this path. I apply all of this, and then UV becomes saturated. Meaning, in the second residual, it is now facing the opposite direction. Make sense?
So is this like a principle
I will explain maybe after class, but we're a little tight on time, so I'm gonna go through the proof. Sorry. So this right here is going to have length equal to the length of the path from S to U plus the length of the path from U to V, which is just going to be 1, plus the length of the path from V to T. Okay? So it's going to be, I'm saying this symbolism here is saying the length of the path of the shortest path from V to T. Does that make sense? Okay, because again, I've assumed that this is the shortest path that saturates that edge, so all of these have to be the shortest possible. Okay? So then if I look at this, right, we know that I'm not going to be able to get to V through this path, so I have to have some other path that goes to V. How long is that path? Do I have a lower bound on how long that has to be? Yeah.
maybe plus 2 because
So it will be, so the length of this will be at worst, or at best, it could be as short as SU plus 1, right? At worst, it could be the same as this, or as SV, which is going to be SU plus 1, right? So it's going to be at least, so this is going to be, I'll say this is now, this is going to be upper bounded by, or lower bounded by, the path, the shortest possible path from S to V, which we just argued is going to be the shortest possible path from S to U plus 1. Okay? That makes sense? So I'm going to say this is greater than or equal to that also. So we have this, right? And then it also needs to have this path from V to U, right? Which is going to be plus 1. Then it also needs this path from U back to T. And how long does that have to be? Yeah.
PVT.
Yes. So it has to be at least this same length plus 1 because it is, because of the shortest path thing before, this has to be at least that long. So we're going to get this is UT now, which we know from what we just said before is going to be greater than or equal to this, which is PVT, and we're going to call this D, by the way. It's going to be PVT plus 1, and then plus this one too, because I didn't actually add that yet. So all of this is going to be greater than or equal to d plus 2. Okay, so if I label this first one d, you can see that this term appears here, this term appears here, this 1 appears here, and then I have plus 2. That make sense? So that is lemma 2, is that. So we just proved lemma 2. So lemma 2 is that if there's a shortest path, augmenting path that saturates some edge E and its length d, then the shortest path that can unsaturate it is length d plus 2. Okay. Okay. Okay, does that help anyone? Okay. Let me give you one more other fact. What is the longest possible augmenting path? The length of some augmenting path has to be less than v if it is a shortest augmenting path. The longest, shortest augmenting path is length v. If I have something that's longer than that, I necessarily have a cycle. If I have a cycle, then there is a shorter path. That makes sense? So if I have that as longer than v, then I would have something like some, I shouldn't call it v just because I'm doing this. Let's say some x from s, and it must have some sort of cycle. It can be some cyclic path. It goes to t. If it's longer than v, then a node has to be visited twice at least. If a node is visited twice, there is a cycle. If there is a cycle, I can shorten it. So it has to be at least v. Or at most v, sorry. The shortest path is at most v. So given that fact, and lemma 2, what could I say, perhaps? The longest path, or the longest, shortest path, those are only the paths I'm going to add with Edmund-Karp. I'm not going to ever add an augmenting path that is longer than v with Edmund-Karp. And if I saturate an edge, it requires some path that is at least 2 longer to unsaturate it. So what does that mean? Yeah. Sure, in front.
Would it be like E times B?
E times V, what, the whole overall runtime? We're not claiming anything about the runtime yet.
Oh, okay.
Yeah. Right now we're proving some intermediate lemma. Yeah. So the longest possible shortest path is bounded by V already. That's what I had. Question for you though, yeah? There's a question for me? Okay. How about this? How about this question? How many times could an edge become saturated? At most. So based on lemma 2 and this right here, this fact, what can we say about that? Yeah.
At most once.
Not at most once, because it can be unsaturated then resaturated. That's fine. Yeah? Not quite? Yeah? V over 2. So, every time I saturate it, unsaturating it needs a path that's 2 longer. Because I'm only ever choosing larger paths by Edmund-Karp, I'm going to do the shortest path, I'm going to only increase that number. Then the number of times that it can be flipped is the number of times that I can add to, which is V over 2. So the number of times that I could hypothetically flip these is V over 2. That make sense? Any edge. Any edge is only able to be saturated V over 2 times, which is sort of where the speed up comes from, because we know with Ford-Fulkerson, that is max flow times. Now it's V over 2. Okay. From there, can anyone close it out and say something about the overall runtime? Yeah? Not exactly. Nope. So running DFS or running BFS will take OV. We will, to saturate an edge, it can happen at most v times, O of v times, it's v over 2, but O of v times. We're missing something. Does having a saturated edge mean that I have a max flow? No. Yeah?
Every edge can be only for
Okay, very, very close, very close. You have something to say in the back? So not quite. This line of logic will get you to the right place. I think I will maybe. Anyone else want a shot to try to get the prize before I give it away? Before I give the answer away? You're very close. You're very close. Yeah, you want to give it a shot? Okay, so I think we're getting close at it here. So sort of the logic here is that at worst I have to saturate every edge, right? But if I'm just saturating every edge, that's not always the condition, right? There's something a little bit more niche here. But also, how do I prove that all of them will be saturated at the same time if they can flip?
yeah.
So you're missing a little bit of the connective tissue there. Yeah.
You have to saturate every edge.
So we do need to do that, yeah. But that minimum cut, so the claim here is that we need to saturate every edge along the minimum ST cut, but that could be all the edges. We could just have S connected to T, yeah.
Could it be E, V?
Not exactly. It isn't guaranteed that the order that we would saturate them is the same as, like we wouldn't do those first necessarily. We could do random edges. Yeah? The longest acyclic path, what do you mean by that? We can't necessarily do that for max flow. There's plenty of times where we could have a path where we can't maximize everything. We can't saturate everything. So like if I just had yeah, okay, you got it. 0 out of 1, then 0 out of 100. Even just this, right? They won't both be saturated. Yeah. So I think I'll award you one of them. I think you got close enough to deserve this. I think you can. I'll give everyone a little bit of time to consider this at home also. But basically, it does come down to the same sort of logic that at worst we need to saturate every single edge at worst, and we can also show that because we're going by these two lemmas, right? And the claim, the lemma 3 that I said out loud. We're going to saturate one every time, and they can only be flipped every other time, right? And what we'll end up seeing is that basically every 2 iterations, we will have +1 edge saturated, right? We won't unsaturate multiple at the same time. That's a little bit of connective tissue proof you need to do. But at the end of this, that means that our very worst case is each time we augment, we add one, we saturate only one edge, and then we unsaturate them as often as possible, meaning that we would have to saturate every edge, which is O of E. Then each one of those could be unsaturated at most V over T times, could be saturated and unsaturated, meaning after more than that many iterations, they will be saturated. And then to run our DFS is O of E. So overall, Edmund-Karp ends up with O of E squared V. Okay? So very close with the EV squared earlier, but it's E squared V. Now, fun fact for all of you. So this is a slightly involved, like the actual algorithm, the change we made is incredibly simple. We changed DFS to BFS. Done. That's the actual algorithmic change. The proof was a little bit more involved. I wanted to go through another example of a proof that I prepared for a little bit more carefully. This is a good proof. If you want to look it up online, you can follow it if you didn't understand it here or rewatch this. But a little fun fact for you, on project 2, Edmund-Karp is not going to be fast enough, actually, to do this efficiently. So we are going to have to try to design even better algorithms. You can try Edmund-Karp. Edmund-Karp will get you a good amount of partial credit on the test, but it won't work for large enough for the project. Won't give you large enough things. We're going to on Monday talk about faster algorithms. Don't worry about that too much, but if you want to do your own studying, just so that you don't waste your time writing out Edmund-Karp on your homework, you can look at other things. All right. Yeah, sure. Get out of here. Go.
Like absolutely lost today from the beginning.
Okay.
And I just should I like watch a video before discussion on Friday?
I think rewatching videos is probably going to be helpful because you can like pause and you can maybe like find slides or like read the book on the side and follow. But yeah, the problem with long proofs like this in class is if I lost you at any point along the way, then I kind of lose you for the rest of it a little bit, and it, we only have so much time to talk about proof in class. Although I ended 10 minutes early, actually, maybe we could have gotten longer. I don't have a clock, so I just have to guess based off how people are acting. Yeah, I think going to office hours is great. I mean, you can come to office hours on Friday this week. I will go through the entire proof again if you want.
Okay, do I need to know it before the discussion? Then should I look before the discussion too?
You don't need to know for the discussion. I actually kind of forget what the discussion is, but you don't. You don't need to know it.
Okay.
Cool. Cool. So Chloe's in charge of this. If you haven't, did you throw anything?
I was too afraid because nobody was like looking at me, so I did not.
Oh, you didn't want to nail in back then? Yeah. I should have called it out. I didn't think about it. Yeah, so Chloe's in charge of this. I believe it is going to be on Tuesday. It's the day that we chose.
Next Tuesday,
Next Tuesday.
is this for the?
Yeah. It's the only time though, because after is break, so we can't do it during break. We have to do it after break ends, which I'm not doing. So it would have to be before. Yeah. And a ton of people couldn't do it on Friday, so I'm not doing it on Friday either. By the way, there is about, I think, 15 to 20 people who have conflicts, so we actually have a pretty annoying rescheduling. So if that time doesn't work for you, I talked to Chloe. Maybe we'll have a third session, but I don't want to write more exams. Everyone's getting a different exam. Yeah.
Alright, okay.
Yeah, no problem.
So you don't let me guess. I wanted to guess.
You wanted to guess?
You saw it.
Well, you wanted to guess this?
Yeah.
Well, I don't know. You faked me out a minute ago, so I don't feel bad. Do you have a question, or are you just complaining? Okay.
Our residual graph is going to be on the exam.
Yes.
Okay. That's all.
I got a question. Am I complaining? I mean, U is gonna be something like I'm losing something.
Yeah.
Add E squared log E.
Yeah.
In my head, it's like, oh yeah, like to find the choice, it's like log E.
Yeah. There is, I will say, with algorithms and with any harder subject, there is a wide gap between intuition and knowing something. It's a even knowing the theory and knowing how to implement this one is a special case where implementation is easy as hell. But it's a Now I will give you props to you, I guess, but without knowing the full thing, like this proof is, I think you'd argue you'd agree is one of the hardest proofs we've talked about in class. It's a tricky thing to actually prove.
Well,
Yeah.
one thing I'm confused about because
Yeah.
I've heard of Edmund-Karp algorithm, but when I heard it, it's like the shortest path that visits all the nodes, and I'm just confused. Like,
No, Edmund-Karp is the shortest path. Yeah.
between all like.
In fact, visiting all the nodes is actually bad. And the shortest path that visits all the nodes is always going to be n-1.
Oh no,
Like,
like
t minus one.
like when I've learned it, it was like if you want like the main thing is to find the shortest path between all the nodes, like in terms of like cost.
No, this is correct. 100% this is correct.
Okay.
Yeah. Sorry for whoever tied it to you incorrectly.
Because it was like the traveling salesman problem.
Yeah, that's not solved with flow. You can't solve traveling salesman with flow. I can guarantee you that also.
No, not with flow. Isn't that search?
Yeah. What?
Isn't that like a search state? Like one of the ways to solve it is state space.
State space? I don't know what you mean by state. There's a lot of ways you can solve
I
it.
forgot it's solving that, but
Yeah.
for project one, I have 2 extra late days. And you open, or should I just like put it?
If you so what was like?
I was sick.
You were sick?
No,
It's absence form. Absence form is the thing. If you
I have 2 extra days. I'll have 2 extra days. So
Oh yeah, 2 extra days for that. Yeah. So you're still trying to submit like now? Yeah, make a Piazza post with your submission and we'll upload it manually. Cool.
Hi.
Hello.
Can you explain this graph to me again?
Which graph? Like just this?
graph, yeah.
Like R1 and R2?
Yeah.
So this is just saying there's some path from S to U,
Yeah.
is what this squiggly means, is some path.
Okay.
Then there's a connection from U to V, and then there is some path from V to T.
Oh, this is like a direct connection, and this is just some.
Exactly, exactly.
Yep.
So I'm saying if I choose this as an augmenting path,
Uh-huh.
then if I'm saying that U and V are the one that gets saturated
Yep.
via lemma 1, then if I create a new residual, then that will be flipped. Because when it gets saturated, the residual, right, remember this is the definition of residual.
Yep.
So when it's saturated, F equals C,
Oh.
meaning if this is 0, this is C,
Oh, I
right?
see.
So it's flipped
That makes
backwards,
sense.
right? And then what we show with this little like geometry here is that going to here, then back, then going to here is 2 longer. At most, or at minimum, it's at least 2 longer.
Why is it at least 2 long?
This right here is at least 1 longer than this. This is at least 1 longer than this, and I still have to do this.
Oh.
Yeah.
I see. Can you equal to V here?
What do you mean equal to V?
Like you. Why isn't it at least 3 longer?
U and V are different nodes. There's an edge between them. There's no self-edges.
Yeah, but you said it's at least like 2 longer because
Yes.
like this is at least 1 and this is at least 1, but then this is exactly 1, so would it be
No,
exactly?
so it's this path adds 1, this path adds 1, everything else is the same. So it adds 2 overall. Adds 1 because I have to go to V instead, and it adds 1 because I have to go from U to T. And I'm still crossing U.
Why don't you factor in this cost?
So this is the simplest way to prove the thing that I was talking about. There are much more complicated ways to prove the same fact. Okay, maybe hold that thought. I'll answer some other questions. If you're still confused, I'll come back for you. Tomas, maybe you can explain in the meantime if you want.
Just had a quick follow-up. What time
Yeah.
was the makeup exam?
I believe it's 7 to 10 or 7 to 9, but ask Chloe. I don't have enough bandwidth to do the makeup exam also. But yeah, her email's in the syllabus. You should be able to find it. Yeah.
I kind of had a similar question. So, one of my other classes had a conflict with one of my other classes,
Yeah.
and then so they rescheduled that, and then that rescheduled exam is now on the same date and time as this exam would be.
Okay. I email Chloe and tell her that you need the makeup. The makeup is going to be on Tuesday.
Tuesday,
Next Tuesday.
Okay.
Yeah, I believe at 7 to 9, but
Wait.
Yeah.
Isn't the actual exam on Thursday?
Yeah.
Oh, so the makeup is early.
Makeup's earlier. Makeup's also a different exam. Yeah.
Oh, okay, because are many people doing the makeup?
Unfortunately, yes. I think around 20.
Oh, I'm so sorry.
There's a lot. So 2:30 and 3:11 are at the same time. So they had a bunch of conflict, and we got moved, which I think is really annoying because our class
I
is
was
more
trying to
important.
see if I can move my exam review to Monday then, because
Okay.
it's currently like I'm gonna ask them if I can.
That'd be good if you can do it. You can also do it earlier on Tuesday if you want. I think it's because that's 7 at night. So if you do it earlier, maybe
Yeah,
people
but
go.
then people are gonna have classes. I'll try
Yeah.
to.
Yeah. Although we have class also on Monday, so remember that. But I believe so. I think Monday the room is free after class, meaning you could just use this room if you wanted to after lecture, if you wanted to do that.
I mean, yeah, I don't think I can directly control that. I have to like.
No, you can just trust me. I've done lots of this stuff. Just do it. And if this room ends up being taken or whatever, go to another room around here. It's the easiest way to do it. I'll announce on Monday that you're doing a makeup right after if you're okay with that, and I think people will go. It's one of the best ways to get people to go to your office hours. Do it immediately after class.
Should I fill out the actual exam conflict thing on Spire? Should I not even bother?
Yeah, just do it just so that I'll get an email. But if you email Chloe, then that's what matters. The exam conflict doesn't matter, but it's